Now, those numbers that we just saw lead us to define something called the stabilizer numbers. The stabilizer number for each individual string will just count the number of the different rotations in our rotation group which fix that particular string, which leave it the same. Look at this string AAA, AAB. R naught, the identity, certainly fixes it. The identity fixes everything. It leaves everything exactly the way it was before. But any of the other rotations will turn this into a different string. So the stabilizer number for this string is just 1. And the set of rotations that fix it is called the stabilizer group for that string. The stabilizer group will always be a subgroup of our original group of rotations. In this case, it's a trivial subgroup. It contains only the identity element. Don't worry about terms like subgroup if you haven't learned anything about groups. The important thing for us will be the stabilizer number, the number of different strings which fix, number of different rotations, which fix that string. Look at the string BA, BA, BA. The identity certainly fixes it. The rotation R2, if we shift by 2 units, that would just take this and put it back at the end there, and you get the same string. So R2 fixes this string. R4, similarly, take these 4, move it to the back, fixes that string. So the stabilizer group for that string includes R0, R2, and R4, and so the stabilizer number is 3. And this string, this special one, AAA, AAA, is fixed by every single rotation. You apply any rotation to that string, you get the same thing. So its stabilizer number is 6. Now these things are exactly the same identities we saw before when we apply all the different rotations to the string AAA, AAB, we got exactly 1 times the entire orbit. This 1 was the stabilizer number. When we apply all the different rotations to the string BBB, BBA, again we get 1 times the entire orbit. Again, 1 was the stabilizer number. When we apply all the different rotations to BA, 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 we get 3 times the entire orbit, and 3 was the stabilizer number. When we apply all the rotations to AAA, AAA, we get 6 times the entire orbit. In fact, it's not too difficult to see that if you apply all the rotations to any string at all, you'll get the entire orbit repeated several times, and that number of times by which the entire orbit is repeated, this number m here, is exactly the stabilizer number of this particular string. x1, x2, x3, x4, x5, x6. It's easy to see that this should be the stabilizer number because the number of copies of this string itself should be exactly the number of those elements there which fix the string. And then every other element in the orbit will just be a shifted version of that first one by some rotation and will be repeated the exact same number of times. So this number m, which multiplies the entire orbit, will be exactly the stabilizer number for that one string. What are the consequences of that? Well, this is what we just wrote before. When we apply all this rotations to a particular string, we get the stabilizer number for the string times the entire orbit. Here's a separate identity, separate from the previous one, which we're going to combine with the previous one in just a minute. This separate identity says if I apply all of the different rotations to all 64 strings, so here I just use the ... I'm listing one string, another string, all of them. Imagine here we have all 64 strings. I claim when you apply all 6 rotations to all 64 strings and look at all the different things you get, that what you'll get is the same 64 strings Remember, this 64 strings are all the possible 6-letter strings from the 2-letter alphabet. You'll get all 64 strings, each one of which repeated 6 times. Why is that? Well, look, for example, at the string BBB, BBB. It will be, when you apply all the different rotations to it, you'll get exactly 6 copies of this string, and none of the other strings will turn into this one when rotated. Why is it true that every single string of the 64 strings will be repeated exactly 6 times at the end? Well, look at one of these strings here in the end result. Why is it repeated 6 times when you do this? Well, of course, it comes once from the string itself when you apply R0. But it will also come when you take a different string and apply R1. What is that different string? That different string would be R5 times this string, because then when you apply R1 to it, you'll get R1 times R5 times the string, which gets you back to the original string itself. And similarly, there'll be some other string here in this list of 64, which when you apply R2 to it, becomes this string. And so for each of these rotations, there's some string in here which when you apply the rotation gives you the string BBB, BBA. So it will appear in the end 6 times, and that will be true of each and every one of the 64 strings. So we get this really neat identity that says when you apply all 6 rotations to all 64 strings, you get those exact same 64 strings, each one repeated 6 times. And now I want to take this identity that we just talked about and the previous one that involved stabilizer numbers and kind of tell what they say when we look at both of these identities together. I claim that this tells you that the sum of the stabilizer numbers for all the 64 strings, look at the stabilizer number m for each of the 64 strings that we have. I claim that that has to be exactly 6 times the total number of orbits. Why? Just take each string in all of these 64 strings and replace it by the reciprocal of its orbit length. We already saw what happens when we replace each string by the reciprocal of the orbit length. If we do that here at the end, replace each string by the reciprocal of its orbit length, we know that this sum becomes the number of orbits, and we have that multiplied by 6. So this right side of this second equation is 6 times the number of orbits. But what happens up here when we take each of these strings and replace by the reciprocal of the orbit length? Well, when we take all 6 rotations and apply it to this first string by the identity above, we'll get just the stabilizer number for the first string times the entire orbit for the string. And when we replace each string by the reciprocal of its orbit length, the sum in that entire orbit will be exactly 1. So the contribution of all of the rotations to the first string is just the stabilizer number of the first string. The contribution from the second string will be the stabilizer number for the second string, etc. So the left side of this equation, when I add them all up, gives me the sum of the stabilizer numbers. The right side gives me 6 times the orbit length. So this gives us our first really powerful conclusion. It says the number of orbits for all the strings is the sum of the stabilizer numbers divided by 6. I'm just taking this equation and dividing through by 6. Our goal is to count the number of orbits because that's the number of fundamentally different table seedings. And all we have to do is add up the stabilizer number for each and every one of the 64 strings and divide by 6. 6 here is the length of the strings. And I know this seems strange and abstract. Let's see how that looks when we look at all 64 strings again. Here we have all 64 strings. And I've arranged them by orbits, but that's not going to be too important right now, except I just want to look at all of these. All of these strings that are in orbits of length 6 have stabilizer number of 1. So if I'm going to be adding all the stabilizer numbers, I have 1s for each of these. 1 here, 1, 1, 1, 1, 1. This one I get a 1, a 1, a 1, a 1, a 1, a 1, etc. How many of them are there? There are 54 of these. There you can see that there are just 9 rows with 6 in each. There are 54 different strings, each of which has a stabilizer number 1. These 6 strings here in the next 2 rows all have stabilizer number 2. Remember, each of these is fixed by R naught, and, or actually we haven't computed them, so let's just notice each of these is fixed by R naught, as well as by R3. If you rotate each of these by 3 units, you get the same thing. So they all have stabilizer number 2. This one we already have seen. These two, both of these have stabilizer number 3. And of course, these two, both of these have stabilizer number of 6. So how do I add up all these stabilizer numbers? I have 54 that have a number of 1. I have 6 that have a number of 2. I have 2 that have a number of 3. And I have 2 that have a number of 6. That's 54 plus 12 plus 6 plus 12. That adds up to 84. And the number of orbits is thus just 84 divided by 6. 6 is the length here of each of the strings, and that's 14. There we go. Now, you might look at this and say, sure, that works out, but it's kind of silly. I had to go through 64, checking all 64 of these strings to find their stabilizer numbers and add them up. And at the time, I could have just easily done exactly what I did here and arranged them by orbits and counted the orbits directly. Why do I need to go through all that work to compute the number of orbits? And that's a legitimate complaint. This adding up all the stabilizers is not something that's quick and easy to do if you have a large number of total strings. And you will have a large number of strings if you have string length that's anything above 6. It'll be very large, and you might even have, instead of a 2-letter alphabet, a 3, 4, or 17-letter alphabet, and then the number of strings just becomes astoundingly large, and you'll want some method of counting the number of orbits that doesn't make you check every single string individually. So we're not done yet with the whole Polya-Redfield method, but what we have is a way to compute the number of orbits by adding up the stabilizer numbers of all the strings and dividing by 6 the length of each string. And what we're going to see in the future lectures is that we'll find a different way to compute this exact same quantity, and this different way of doing things will end up being much more efficient.